Hello. We have discussed design methods and also compared them in the last lecture. From now onwards, we look at some finer aspects of compliant mechanisms. One of the very important ones is mechanical advantage, and that is what we will discuss in this lecture and the one after this. So, what we will discuss is a set of aspects that one needs to worry about in terms of mechanical advantage. For mechanisms, compliant mechanism is a mechanism. The most important thing is transmitting force and of course motion. When you are transmitting force, you need to have mechanical advantage. In fact, the principal use of a machine, any machine, is actually to give an advantage to the human being. So, here compliant mechanisms as tools do exactly that. So, we need to discuss how much mechanical advantage, that is, with very little force you want to accomplish a task of handling a big load. That is what mechanisms do, all of them. So, or machines in general. In this case also we look at how compliant mechanisms mechanical advantage can be looked at or can be analyzed or even develop an optimization method to get a mechanical advantage that is good for a given application or even maximize mechanical advantage. So, let us look at the aspects of mechanical advantage in compliant mechanisms. So, the principal reference for this work is a master thesis at Purdue University by Brent Salomon, and Professor Ashok Midha was the advisor of this student, and they have a very nice paper. In fact, the master's thesis itself was an excellent thesis that looked at, as it says very humbly, just an introduction to mechanical advantage, but all that one wants to know about mechanical advantage is in this I would say 4-page paper, 311 to 315, and that is what we will discuss today. What was in this paper, what are the nice things that Ashok Midha and Brent Salomon had come up with. In this paper has more details, but it is a 4-page paper. We would highlight the important aspects of mechanical advantage that they discuss in this one. As you may recall, Professor Ashok Midha is the one who coined the term compliant mechanism and had done some very fundamental work at the very beginning of the field, at the inception of this field. One of the great things he has done is to analyze mechanical advantage in a way that is very insightful, as we will try to discuss today. Okay. Let us first define mechanical advantage. Mechanical advantage, acronym AMA, mechanical advantage, is simply output force divided by input force, as simple as that everybody knows. Even in high school we are taught, when we talk about levers, we will say what is a mechanical advantage, output force divided by input force. Okay. Now, Salomon and Midha gave a formula for mechanical advantage of compliant mechanisms. So, that is this one. Its mechanical advantage is there is some delta in by delta out minus delta SE by FIN and delta out. How does this come about? So, that is what we will first discuss. So, before this, let us actually see what this delta in, delta out and all that is. So, let us look at two plots. Let us say there is input displacement and then input force FIN, UIN, and then F out and U out. So, if you have a compliant mechanism, you have input force and input displacements, there could be some curve there. Similarly, F out and U out, just so it looks different, I will draw a curve differently. It can be anything, it can be stiffening, softening, whatever. When you have this, when we look at this formula, what we mean by delta UN is that this mechanical advantage of mechanisms in general, they are not constant throughout the range of motion. See, any machine or mechanism that has motion, it is going to move at different configurations. You will have a changing mechanical advantage, it is not going to be constant. Maybe for a simple lever where it is a fulcrum, it will be constant. but not in general. So, if we have such a situation where things are changing, we should look at, let us say, a particular point. Let us say I take a point here, there is some u in, and correspondingly there is, let us say, there is some u out, the corresponding point over here. Okay. So, this point and this point correspond to each other. So, you have some f in and then u in. Now, if you want to define mechanical advantage, what we will do in the derivation of this particular formula, consider what if there is a small change in the input displacement, that is our delta u in. Similarly, there is a small change in the output displacement, that is we are moving, this is delta u out, this is delta u in, delta u out, which is what we have here. Okay. And then we have delta u out again, of course there is Fi in, there is no Fi F out in this formula. There is also delta SE, delta SE for us is strain energy, because in a compliant mechanism deforms, there will be energy stored in it, elastic energy, which you call strain energy. So, when you go from one point to a new point, there will be some extra strain energy stored, and that is this delta SE. SE is in general strain energy. When you just imagine that from a particular point that you are at, if you slightly go to another configuration, there will be an additional strain energy that comes in. It will be positive or negative depending on whether unloading or loading, but there will be a delta SE, that is what is shown here, and all of those define the mechanical advantage of a compliant mechanism, as was done by Solomon and Medha. The way they derived it was as follows. This is what we need to derive. So, the first thing you do is look at the change in work, both the input work and output work. So, I will circle this part, which is the input work, and then circle this, which is the output work. So, input work has a positive sign, output work has a negative sign. That makes sense, because output is going out of the system, input is coming into the system, where the system is compliant mechanism. Why is this F in plus half delta F in u in? For that we need to go to these charts here, the plots that we did, we are basically talking about this. Okay. So, this portion, this rectangle will be F in times delta u in. So, what we have here, F in times delta u in. The other part, half of delta F in times delta u in, is this little portion. So, I will just fill it. Basically area under this is what we are looking at when we say we have the input work. So, this entire area, if I take that, that will be delta W in. Similarly, if I take this other one and take this entire thing here, so this will be delta out. Okay. So, the energy balance, if you do work and energy joule balance, if you do this delta W here, now we have this and we have that. Now, we are actually making a small approximation, that is delta F in and delta U in is a second order quantity, same thing delta F out, delta U out, then we just take F in into delta U in minus F out delta U out. In other words, we are only taking this portion, that is we are taking only this much rectangle and leaving out that little part in both cases. So, this is F in times delta U in, F out times delta U out. Okay. That is an approximation, that is why we are showing the approximation. Now, this delta SE should be same as this net work that you have. You are putting in some work by input force, taking out some because of output. The difference has to be equal to the energy stored in the compliant mechanism. In other words, delta SE should be equal to input work, that is F in times delta UN, and then minus F out times delta U out, okay, that is delta SE. Okay. Now, delta SE is equal to F in times delta U in minus F out times delta U out. Now, from here if you rearrange this equation, F out by F in will turn out to be delta U in by delta U out minus delta SE by F in delta U out. Basically, the formula that we have here is easily derived in this manner. Okay. So, here there is a notion of looking at mechanical advantage, that is this one has two components, they are both indicated here. We can call this MAR, that is the rigid body or kinematic component of mechanical advantage, and there is including the minus sign, that is an important thing to say, including the minus sign is compliant or elastic part of the thing. So, we have MA rigid body which is simply delta U in by delta U out. Instantaneously the mechanism is the reverse of forces, right. So, F out by F in is mechanical advantage. So, delta U in by delta U out is the mechanical advantage also, that is the rigid body part. And then MAC, that is the compliant part, is minus delta SE divided by F in and delta U out, it is the compliant part. Notice that the compliant part is actually negative. So, the compliant mechanism's mechanical advantage is going to be always less than or equal to MAR, that is one observation Solomon and Meadha made. That is actually clear because part of the input energy is stored in the compliant mechanism. So, both the efficiency and mechanical advantage will be hampered compared to the corresponding rigid body linkage if there is one. Okay. But then within compliant mechanism itself, the kinematics is clearly present, that is something we have been saying in this course. So, compliant mechanisms are not different from rigid body linkages, they are not different from structures also, they are in between. So, here inherent kinematics exists and we have that coming. So, we use simply energy arguments here, and to show that mechanical advantage has a kinematic part and elastic part is actually quite interesting, and we will see more of it in this lecture how it comes about. There is a rigid body or a kinematic part and there is a compliant part which is negative. Okay. It looks like a disadvantage right now, and then in the next lecture we will see how we can overcome this seemingly disadvantageous position that compliant mechanisms have. Their mechanical advantage will always be, so I can say because second one is negative at this point, MA is less than or equal to MAR for a compliant mechanism because this is negative. So, we will see how we can make that positive also later, but for now let us say that this is an insight. In general this is true unless you do not do something extra or special. Okay. That is the first thing we have to understand, and let us understand this formula more, right. We have this rigid body or kinematic part and then an elastic part, and look at the terms what are there, delta U in, delta U out, that changes from position to position because that is why I have taken this incremental displacements here and incremental strain energy as well. Okay. If you want to make the second part also positive, F in and delta U out they will be positive because you would have assumed a direction for input force and output displacement, they cannot be negative. If they are negative, your main function is not being served. Delta U out, if you make it negative, it is not going in the direction you want, it is going somewhere else. So, that is not good. So, their signs cannot change. What sign can change? The sign of delta SE can change, that is as the compliant mechanism deforms, it actually has its strain energy decreasing. If you have such a situation, then you can actually make the compliant part also become positive. So, overall mechanical advantage can increase. That is the modification that we will discuss in the next lecture, but right now just remember that unless you make delta SE negative, your mechanical advantage compliant mechanism is always going to be less than the kinematic part of it or rigid body part of it. So, we can also rearrange to understand a few things. So, delta in by delta U out, if I just take that as out common between the two, I can rewrite this as delta SE by F in the delta U out. I think there are some more things I have to do delta SE F in delta U out. I have taken delta, so I have to actually multiply, right. So, this will become delta U out and then delta U in. So, that when you do. So, basically this is a typo, this should be in, okay, and this should also be in, then it will be correct. When you multiply, these things go and then you get delta U out there. Okay. So, we can take basically MAR and show that 1 minus delta SE by this. Okay. When you do that, again you see this is a negative quantity, it will always reduce unless you make this negative. Okay. That is something to note here. And Solomon and Mither defined this something called FC, what they call force or force due to compliance. That is, when you have a compliant mechanism, unlike rigid body linkage, the input force is used partly to deform the mechanism, to store energy. Basically, motion comes in compliant mechanism because of elastic deformation, force is needed, that is what they call FC. And FC, if you see from the formula here, is delta SE by delta U in from here. Okay, that is what they define as FC, okay, force that is needed to just deform the compliant mechanism, so that you can make contact with the workpiece. So, that is not really helping in the mechanical advantage to apply force on the workpiece or an object that you want to hold. So, that is actually one minus that it comes. The more FC is, the less the mechanical advantage is going to be. That is something that one needs to understand, but then again we emphasize that that can be made negative in some cases. Okay. Now, also let us understand what happens in the limiting cases. We will consider two limiting cases. One limiting case when there is no elastic deformation. So, whatever we derive for a compliant mechanism, we should be able to generalize it or make it specific to rigid body linkage, in which case there is no elastic deformation. So, this goes. So, you get delta in by delta out, that is essentially mechanical advantage of rigid body linkages. So, our formula is correct. Again, compliant mechanisms lie in this continuum spectrum between structures and rigid body linkages. So, in that sense this formula holds good. What about the other extreme, which will be interesting to look at? So, what if there is no output displacement? What does it mean? You have a compliant mechanism which I have here. Let us say it is a gripper. So, when I apply, it is fixed at these two locations, and this is like the jaws that come together. So, when I apply force, it goes like this. So, initially when let us say my object is a small object, and until I touch, I need this FC, the force, just to make contact with the workpiece. I have not done any work on the output. After it touches, then I start doing it. Okay, now, if I look at this configuration, just after touching, just after I touch, then there is no more output displacement if my finger is to be rigid. That is, very stiff object, if it is there, there is no more output displacement. If there is no output displacement, we have a little problem here in the formula, because we have output displacement in the denominator. So, does it mean that this formula is not applicable? It turns out that in that particular case, the numerator that we have, if we take out this thing here, if I take delta U out, then what I get will be delta U in minus delta S E by F in, right. So, if you look at this, when this becomes 0, there is no output displacement, then we would say it is infinite, mechanical advantage is infinite. It is not, because the numerator here will also be equal to 0. The reason is, as we had seen in the derivation, the delta SE, the change in the strain energy, is equal to the input work and then minus output work. Now, there is no output work because output displacement is 0, input work is the F in into delta U in. So, this is also equal to 0. So, in the limiting case, if I take the limit of this when output displacement goes to 0, will be finite again, and that is given in this manner by introducing this f out. So, we see this f in, because it is 0, f in is delta S e by delta u I n, that is what we have put here. Again this is f out by f in. What is f out? Whenever you have a rigid workpiece, over that compliant mechanism is interacting, there is no displacement, there will be reaction force, that is your f out, that is the reaction at the fixed output, at the fixed, because we are there is nothing like rigid, but very stiff object at the fixed output point. So, there fixed output point you have some f out divided by f in, you can talk about mechanical advantage there. So, it is not like it is infinite, because both the numerator and denominator go to 0 when output displacement go to 0. This is something that we need to understand. The formula is actually foolproof. Now, Solomon Meader defined 3 types of mechanical advantage, and the first in each type something remains constant. What are the things that we need to consider? We have input force that is varying, we have output force that is varying. In addition to that, we also have workpiece stiffness, because as a linkage or a mechanism we have to interact with the workpieces. Some of them may be flexible, some of them may be stiff. So, that workpiece stiffness, which Solomon Meader used the symbol Kw, and we have been using K external in our SL model, SML model and so forth. These two are the same symbols, 2 symbols for the same quantity. So, depending on what you fix, you want to fix input force, you will get one type of mechanical advantage, fix output force, or maybe even output displacement, or maybe input displacement. There are all these parameters, or for given workpiece stiffness you will have a mechanical advantage. To take care of these things, Solomon Meader defined 3 types of mechanical advantages. First type 1 mechanical advantage is for fixed output displacement, that is u out is fixed, u out is fixed. For a compliant mechanism, if you want to have this much output displacement, as you vary the input force, mechanical advantage varies. So, here input force in the x axis for fixed output displacement, for each output displacement there is a separate curve. Okay. So, this is the one, you get several curves, a series of curves. These curves are always very useful, because they give you insights. Here what do we see? As output displacement is increasing, mechanical advantage is decreasing, and sometimes you can even go negative, meaning that output or input, they are going the other direction, output force, input force. So, after that, this is 0 already, if I were to extend, it actually goes negative. What does it mean? That instead of resisting output load, it needs additional force to move by that much displacement, that is what it means. So, if you have an object, you are applying input force, it should press the object and apply force on it. But here if it goes negative, it means that you need additional force, output load is not resisting, you have to apply additional force over there. So, that is not good. So, they do not even show the negative mechanical advantage, that is not an advantage, it is a disadvantage. Okay, but you can see that as you want more and more displacement, you have decreasing mechanical advantage, goes in a nonlinear way as well with input force. In fact, what Solomon and Meader's paper gives is that you can write it as there is a limiting mechanical advantage, that is MAS, all of them are going to, like this one has gone asymptotically, if you extend farther enough they are all going to some value. They define it as bounding mechanical advantage times 1 minus Fc, that is the force due to the compliance part, that is deforming the mechanism, Fc by Fi in, right. You can actually fit that to this model. They were all numerically done, but you can fit this model because there is inherently this behavior in the compliant mechanism. Let us look at type 2. In type 2, for different forces, so you fix the input force. So, input force of 1, 2, 3, 5 whatever, you get different ones. So, here now output displacement is varying, not output force, output displacement is varying, and then you have mechanical advantage. And you can look at both of them together as well, type 1, type 2, 3 parameters. You have F in and then U out, they use DO, it is from their paper. Mechanical advantage, both type 1, type 2, you can imagine like a surface. Okay. The slices of this, that is fixing F out, you will get one slice, fixing F in you get another slice, is what we consider type 1 and type 2. There is a type 3 where you would fix stiffness at different value, 0, no workpiece, 100, 200, some units, and going to all the way to infinity. With regard with different input force, you can get the mechanical advantage. Okay. They look pretty much constant here, but actually they are not, they are slightly varying, but in this big scale we are going from 0 to infinite stiffness, infinite meaning it is completely rigid workpiece. Okay. The type 3 mechanical advantage. Another way to look at this is workpiece stiffness, you vary and get this limiting value, finally it goes to, all of these curves go somewhat like this, as in practically if you plot that value here, you can see that as workpiece stiffness increases, mechanical advantage is actually increasing. So, these curves are also useful, and this one can be put into a form which is what Salomon Meadha give, that is again bounding value of MAS, and then there is workpiece stiffness, there is a sigma that they use which they call sensitivity, which we will discuss now. The sensitivity, that is sensitivity of the compliant mechanisms to the stiffness of the workpiece. Compliant mechanism mechanical advantage, or for that matter even rigid body linkages, kind of it will be a function of the workpiece, more so with compliant mechanism, because there is inherent elasticity and its kinematic characteristics will change. For rigid body linkage, kinematics defines a mechanical advantage. For compliant mechanisms, there is a compliant part, depending on whether the object is stiff or flexible, its mechanical advantage changes, that is captured by this sensitivity. Okay. In order to understand this, we move on to another reference, which is a ME project at Indian Institute of Science by Mohit Mathur a couple of years ago in 2014 he had done, where whatever we saw with mechanical advantage that we saw with the external stiffness, how mechanical advantage changes for a compliant one that is given is shown here. Okay. So, Salomon Meadha had done one more thing, which is to depict in a different way. So, you see mechanical advantage shown against output displacement or various output forces. Now, you put various output forces. This is useful because if you have workpiece, you would know, let us say it is a linearly modeled workpiece, meaning workpiece has a like a spring, linear spring, then you would know the force and displacement, some Newton per meter. So, let us say some x Newton per meter. Then you would see, okay, if output force is let us say 20 and corresponding displacement if you have 0.6, you would know. So, if you have x Newton per meter, how much deflection? So, you have force by x, this is stiffness, you will get some output displacement. So, you go along this whichever, let us say this value, then you would know if for that output force what the mechanical advantage is. So, for various workpieces for a given compliant means, if you draw these curves, you can see what mechanical advantage you would get depending on the workpiece stiffness. This is another useful way to depict MA. Mohit Mathur had done some work on understanding this sensitivity that we just discussed, that is over here, what that sigma is, how sensitive is the workpiece stiffness to how sensitive is the mechanical advantage to workpiece stiffness. So, in fact, he had looked at this spring lever model, because that is a model of the compliant mechanism. We wanted to see whether it captures this mechanical advantage. So, using that, because everything can be done analytically, again writing potential energy, writing the equilibrium equations where we can solve for U out and F in, put them back into the mechanical advantage formula. This is F out by F in, you get a formula like that, and this formula can actually be put into this fashion. with just rearrangement, which we will see in the next slide. So, if you want to get mechanical advantage in this way, where that sigma that is there Sk, we are called about sensitivity using Sk, but equivalent to what Solomon Midha called as sigma, that MEIS is given by this and sensitivity is given by this. Now, if you look at these two, you would understand that how KCI, KCON need to be adjusted in order to get a sensitivity. You do not want sensitivity to be high, because with all kind of workpieces you should get the same mechanical advantage. You want sensitivity to be low. At the same time, MEIS that you get, basic bounding mechanical advantage, you want it to be high, and in fact these two are also related, which this analytical model tells you. If you look at these two equations, you would see that MEIS is actually related to Sk with this n by KCI. It does not mean that MEIS is high when there is n is high. We have n is geometric advantage, inherent geometric advantage, right, if you remember lever ratio. If n is high, you think MEI is high? No, because Sk has in the denominator n square. So, when you plot it, you would know that when n increases, it does not necessarily increase MEIS, but you see what influences sensitivity, what influences MEIS. And if you do this for different mechanisms, as Mohit had done, you can see that a mechanism that has high MEIS has some sensitivity. If I go to another mechanism that has, let us say, low MEIS, also high sensitivity, this is actually very bad in a way. Okay, it is a gripper, it does not have mechanical advantage, whereas these are the ones that can actually crush things over here in the output. This is the output here, this is input. Okay. So, we look at this MEIS and Sk, can talk about not only mechanical advantage, but also we can talk about sensitivity to the workpiece stiffness. Okay. So, based on this, Mohit actually had post optimization problems. One is minimize negative MEIS or maximize MEIS subject to a limit on the sensitivity, or minimize sensitivity subject to at least some MEIS star, that is some basic mechanical advantage you should have. MEIS star is less than MEIS, meaning MEIS is greater than MEIS star, that you have two ways of posing the problem, and that is what he had done, and which when you get in terms of this KCI, KCON tell you a lot about how to design it. So, with mechanical advantage, with the work that was developed by Solomon and Midha, one can go a little farther, and let us just summarize. It is a very important aspect of designing compliant mechanisms, that is mechanical advantage. It has rigid body and elastic or compliant part to it, and three types of mechanical advantage can be defined based on workpiece stiffness, input force, input displacement, output force, output displacement. More important, sensitivity to the workpiece stiffness is an important aspect that we need to remember, and we can do optimization for the trade off, and inherently it is disadvantage of compliant mechanisms when it comes to mechanical advantage, but as we will discuss in the next lecture, it is not so. If you take a little more care, it cannot always be done, but in some cases you can actually make the mechanical advantage higher without actually reduce the mechanical advantage. So, the further reading for this very nice paper and this report of Mohit Mathur, and that a little bit more we will discuss in the next lecture. Thank you.